Okay, so this is the chapter 4 test review for Trig. Take them one at a time. Number one just says this, and I will change the number, but I won't change the instructions. It says, find the radian measure for an angle whose measure is 115, we'll say. So they're going to give you it in degrees. It says, find the radian measure for an angle whose measure in degrees is 115 degrees. So that's what you get. How many radians is that? And I would expect the answer to come out in terms of pi, if possible. What, pardon? I'm sorry?
Don't touch you. 115 times pi divided by 180.
That's correct. Did you hear what Andrew said?
So 115 times pi divided by 180.
Okay. How do you know it's pi divided by 180 and not 180 divided by pi? That's the conversion factor. That or it's reciprocal every time. How do you know which one's which? Yeah. So
Radians is the opposite.
you're right. We're going to multiply by pi over 180, or multiply by pi and then divide by 180. Same thing. But how come you chose that and not 180 over pi?
You're trying to make it a smaller number. Because it's less.
You're trying to make it what?
Smaller number.
Yeah. And this is a very small fraction. 3 over 180 is pretty tiny. That will make this smaller. Degrees and radians. There's always more degrees than radians in an angle. Always. Right? There's only 6.28 radians all the way around. There's 360 degrees all the way around. So if you're wondering, is it pi over 180 or 180 over pi? That's one way to decide. The other way to decide is whenever you're converting to radians, generally, not all the time, but generally there's a pi in the numerator, like 3 pi halves or 5 pi sixths, right? So choose the one that will leave a pi in the denominator or in the numerator. Then you'll have it. Then you should fraction so that you can leave the pi in it. So 115 divided by 180, your calculator can do that, give you a decimal, then you go math, enter, and gives you what reduced fraction?
23 over 26.
So it's 23 pi 26. That's what I would expect to see. Everybody cool on that? You good? Now, converting from radians to degrees is even easier. I'm not sure that's called for, but just in case you're wondering, if I had 4.87 radians, how do you convert that to degrees?
Times it by 180 and divide by.
Yeah, we're gonna. Okay, let me change my mind. Give you the radians like this. 25 pi 27ths. How many degrees is that? What would you do? If you're going to multiply by a conversion factor and you can't remember what, you should multiply by the one where the pi's will cancel. Right? But for me, when I do it, I just remember pi is 180 when I want to go to degrees. So I just leave this off and I just multiply 25 times 180 and divide it by 27. Just another thought. Okay? All right. Anyway, first one calls for you to convert a set of degrees to radians. Please put it in terms of pi and reduce the fraction.
I'm so confused. I don't understand.
Take 115 divided by 180 and then change that to a fraction. So
There you go. I put in the pi. I was like,
Oh, okay, yeah. Yeah, don't put the pi in, just let it tag along.
How do you put that? How do you do the change it to a fraction?
Math, enter. Enter.
Oh, okay.
The reason I have to hit enter is because you gotta go to the math menu, choose fraction. That brings it back to the home screen. Then it says, okay, so you want me to change it to a fraction? You say, yeah, that's what I said. So you have to go enter. There you go.
So 23 over 36 or 26?
23 over 26.
Is this correct? 23 over 26?
36.
Oh, 36.
Oh, wait.
Is this 36? Did I just hear you wrong?
Yeah.
Okay, sorry about that. So 23 over 36 is what the reduced fraction is? Okay, sorry, whoever's watching, it's 436. Goodness, that number one took more time than I wanted it to. Are you ready?
Yep.
The next one says, you're using a simple pulley. One pulley. If you use a whole bunch, then you can lift ships from water, according to Archimedes. But we'll just do that one. That's a whole other story for physics. Okay, so a simple pulley of radius 1.5 feet, that's a big pulley.
What was it?
1.5 feet, the radius is 1.5 feet, is used to lift heavy objects. Determine the height to which the object is lifted when the pulley rotates 520 degrees. This is all made up numbers.
Say the last one one more time.
Yes. Determine the height of the object determine the height that the object is lifted when the pulley rotates, what did I say?
1.5.
520?
Yeah.
520 degrees. Do you understand what's being asked? You know what to do?
What did you figure out, like, the circumference?
You could.
Yeah.
Could do that.
2 pi r.
510 degrees is more than one circumference, but not two, right? So how are you going to think about this? Circumference is a good notion. You could do it by thinking about circumference, but there's more than one. We can figure out exactly how many circumferences there is by doing what? Yeah, 520 divided by 360 would tell you how many circumferences that rope has traveled through as it's going through the pulley. And then what? Multiply that by the circumference.
1.5.
No, the circumference is,
Oh, 2 pi r.
no, it's 3 pi. What's the circumference of a circle? What's the equation? The formula. 2 pi r, what's r?
1.5.
What's 2 times 1.5?
3.
Then what's the circumference?
3 pi.
3 pi. So 3 times 3 is 9 point something, so you would take that fraction times 9 point whatever, times 3 pi. I would tell you how far it was lifted.
Do you want it in like decimal form or in terms of pi?
No, decimal's fine. The reason why decimal's fine is because they gave you the information degrees, and they will on the test too. Here's another way. You don't have to do it this way. I'm just giving you another option if you didn't understand what Akira and some of the others were talking about.
So you just.
Andrew and Akira muscled it through by reasoning, which is great. It's awesome. There is a formula you can use, though, if you know which one to use. And it is that one that said L, which is the arc length, even if it goes around more than once. L is equal to m pi r over 180, and that's the arc length when the degree, when the angle is given in degrees, which is in the measure of the angle, we call it with m. So we could do this by taking what did I say, 520?
Yeah.
520 pi times 1.5 over 180. That should give you the same answer. Check it out for those of you who reasoned it, and maybe use this and see if you don't get the same thing. Yep. Okay. So for those of you that are wondering about the reasoning, just really quick, if this is the pulley, the rope is going to start by going through here. If it goes, if we pull that until this mark ends up being right where it is again, we've gone 360. That mark's going to end up over here. 360 and 90 is what? 360 and 90. 4. So I'm saying, I think I'm saying that the angle is going to be over here. Is that right? The 510, the 520? Okay. So we have gone one full circumference and this much more, if you're reasoning it through. So you find out what this fraction is, or you find out the fraction that is 520 over 360, which would account for the whole thing. And that fraction will be improper. And multiply it by the circumference, because it is that fraction of the circumference that the pulley is turned, which is what the rope is lifted. Or you can do it this way, because it was given in degrees, you can use this. You can even use this if you want as a formula, but you've got to convert 520 degrees to radians first, because this doesn't work unless theta is in radians. So you could do that too.
So pretty much all you're doing with that equation is multiplying the radius by the degrees radians, pretty much.
Yeah, that's what we said before. What we are doing is we are multiplying the degrees times the conversion factor to change it to radians. That right there will change 520 degrees to radians because that's the conversion factor, is pi over 180. So that's radians, that's theta, so it's r theta. Or you can memorize this. It's the same thing because it's converting the degrees to radians by multiplying by pi over 180 right there. And there's your r. So S equals r theta or L equals this. You want to memorize two formulas? Go ahead. They are just alike. It's just you have a conversion factor here. You have to change the degrees to radians and then use it here in this one. This one's an easier one to memorize. But this has to be in radians. You have to remember how to convert it. Whatever. Lots and lots of ways to think about this. They're just muscling it through with reasoning. I like that a lot. Shows you know what you're doing instead of just recalling something.
Wait, so how did you do the reasoning one?
What?
How did you do the reasoning one?
The pulley, the rope's going to come up from here and it's attached to something down here that it's going to lift. And it's going to go through one whole turn. That would be 360 degrees.
Yep.
And then a bit more until it has turned 520 degrees altogether. So what we're saying is that 520 divided by 360 is the fraction of the circumference that has been spun. And it's more than one because this isn't proper. Times the circumference. That fraction of the circumference is how far the thing has spun, which is 2 pi r. That's the reasoning to me. It's a fraction of the circumference, and this is the circumference. So this process right here should give you the as far as it has spun. I mean, you know what I'm saying? It's gone around more than once. There's your more than once. It's that fraction of the circumference times the circumference that it has spun in 520 degrees. And besides that, look what happens here. M pi r over 180. It's all there. Even with the reasoning, comes up with that formula. It all meshes together. It's all correct.
That's really cool, actually.
What's that?
That's really cool, actually.
Yeah, it is. Think about it, reason it through. And what you're doing by the reasoning, which is awesome, really, truly is awesome, is you're coming up with this formula again, but you're doing it by reasoning instead of just having somebody hand it to you and memorize it. Either way, you'll get the right answer. But whether you want to memorize something and say, I don't know what this has to do with anything, or whether you believe this and you see the reasoning and say, that's where that came from, that'll stick longer. I'm just saying. All right. Again, too much time on number 2. Are you okay with this?
Yeah.
All right. Number 3 gives you a right triangle where the legs are given to you, just the legs, and a marker that indicates it's a right triangle. And one of the other acute angles is marked, and they want you to find all 6 trig functions of it. So I'm going to erase this for the sake of people watching so they don't get too much in their screen. And so we'll give you a triangle, not necessarily on a unit circle or anything like that, just a triangle, a right triangle like this. And they will give you, they'll tell you, for example, that theta is here. And they will tell you the lengths of the legs. Let's say that this is 15 and this is 18. And they'll give you that information, and it says, evaluate all 6 trig functions of the angle theta. What do you got to do first? Find the hypotenuse. And I would really like that hypotenuse in simplest radical form, not a decimal. As a matter of fact, if you don't put it in simplest radical form and you calculate with a decimal, and even if you're right, it will cost you a point on this problem. Now, I have no idea. I made these up, so the simplest radical form may come out pretty ugly, but I think it's not too bad. So you would take 15 squared and add 18 squared, and that would be 225 plus 324, which is 549. Is that right?
Yeah.
And then you would attempt to prime factor that. Does anything come out of that?
Oh, yeah.
3 does.
3 does? Okay, and that would be 1, 8, 3?
Yeah.
Okay, and then does that 8, 9, 10, 11, 12, yeah, 3 will go into this. That'll go 61. Is 61 prime?
Yeah.
I think 61 is prime. So this was a really crappy example to choose. It probably won't be that crazy with a prime number that big, but whatever. This is going to be 3 root 61. right there. Y'all see where we come up with it? Okay, so once we have that, then we just start going after the trig functions. I know, do you want me to list them all? I guess I will. Sine of theta is gonna be 15 over this, which will be 15 root 61 over whatever 3 times 61 is. I don't know. Anyway, it turns out to be this. It's 15 over 3 root 61. And you know what? I think I'm not going to make you rationalize that. Can if you want. I'm not going to make you. I'm so sick of that rule, and there's no good reason to do it anymore, except that your professors that you have in the future will want you to do it. And you all know how, right? And you don't have to do it for me. It's dumb. Which is one of the reasons I don't want people at ISU to see this video. Cosine is going to be 18 over that. Oh, by the way, I will ding you for this. You can leave the radical in there, but I failed to finish this. You need to write it as 5 over root 61. You are required to simplify fractions. And radicals. I made you simplify this radical, but you don't have to rationalize them anyway.
That'd be a lot simpler
To rationalize, yeah. 5 over 61 over 61 will be fine. And you can list it that way if you want. I will also give you full credit for this. But I won't give you full credit for this. Okay? So the next one is 18 over that, which reduces to 6 over root 61. The tangent is an easy one. It is 15 over 18, which is 5 over 6. And then we turn them all over. Cosecant. What's cosecant of theta? Root 61 over 5. Secant. Root 61 over 6. And tangent, or cotangent. 6 over 5. Okay. One kind of unfortunate thing about the way this is listed in the answer column, they do not have them listed. This is the way it's listed on your answer. See those 6 things right there for this one? They don't have them listed like I do, where you have a function, well, a trig definition and its reciprocal side by side. It goes sine, cosine, tangent, and then it does 3 more. So make sure you're looking at the right one when you do it. It won't be side by side like this. I would recommend you do sine, then cosine, then tangent, get those, and then be very, very careful. If they ask you to do cosecant next, make sure you're looking at the sine one. If they ask you to do secant next, make sure you're looking at the cosine one. I think they kind of do that on purpose to make sure you remember which reciprocals belong with which instead of just have them organized like that. You don't just tip these over to get these. Make sure you get the ones that belong with which one. You follow? Yeah. All right, number 4. Number 4 says to solve triangle ABC for all its unknown parts. So what they're going to do in this triangle, there are 6 parts to every triangle. There are 3 angles and there are 3 sides. And with any right triangle, they will give you 3 things that are known and ask you to find the other 3. And they can give you the 3 things that are known in many, many combinations, and you got to figure out how to find the other 3. One of the 3 things they will always give you is the right angle. Otherwise, none of this applies. Okay, so, and it's really weird the way this is done on here, and I will put it on here like this so that it doesn't spook you. This is triangle ABC, and they put it, this is A and B and C, and they label it that way. And then they have little letters, little a over here, little b over here. So the little ones are opposite the big ones, and little c here. And then they have, this is angle beta, and this is angle alpha. There is no reason for these to be here. Don't let it bother you. You can call this angle A or you can call it angle alpha. I don't care. It's the same thing, and it's redundant to put them both in there, but the author does it. I don't know why. And then it says, solve triangle ABC, capital ABC, for the unknown parts if, and I'll give you a combination that will work out here. If A is 12 and beta, we may list it that way, beta is 49 degrees. And that's how they will list it. something like that, and then you will put the things in. I write it right in the triangle. So A is 12. I'm gonna just write equals 12 here. And then beta is 49. I'm gonna put 49 degrees here. Those are things that are given, and I've got to go find. I got to go find capital A or alpha, whatever you want to call it, and little b and little c. So it listed in the answer column. Yeah, they refer to any angles that you have to find with alpha and beta rather than capital A and capital B. It's no big deal. It's just redundant. Okay, so how do I go about finding? So what do you want to find first?
Beta, alpha.
Yeah, alpha would be the easiest thing to find. And so alpha is equal to 41 degrees. That's an easy one. And since that came out nice and whole and is not approximated at all, you can actually use that in future calculations if you like, because there's no approximating with it, and that's good. So I'm going to put that in there, and we can use that if we like. Okay, so if I want to go, what do you want to find next? B. Okay, so if I go after little b, what function do you want to use? Do you want to use? Yeah, we're going to have to use tangent because we don't know anything about c yet, and sine and cosine require a c to be known. Okay, so if we use the tangent, you want to use tangent of 49 or the tangent of 41?
41.
You do? Let me show you. Just
Oh, yeah, no, sorry.
No, we want 49.
yeah,
Yeah.
one of them is more efficient than the other.
Yeah.
You can use either one, but one has a more efficient solution. If we choose 49, let me show you what's going to happen. If we do the tangent of 49, it's going to be b over 12, and the cross multiplying will give it to you immediately. If you use the tangent of 41, you see if we choose that, it will give you 12 over b, which is fine. It's just that you're going to have to cross multiply it and then divide. Whereas the other one's more efficient. Doesn't matter. Just show your work. That's what matters. So we go back to the 49 for efficiency, and we have b over 12. And then we take the tangent of 49 and multiply by 12. And what could happen here to give you a wrong answer? The mode. Be sure, because you're going to be switching all over on this test, because this chapter talks about both. Sure, you're switching your mode to degrees. What?
Are we in degrees on this?
We have to be in degrees because that's how this was given.
Yeah,
13.8? Really? Oh, yeah, that would work. I thought we were looking for an angle for a second. I'm going, there's no angles that small. Okay, 13.8. All right, to the nearest tenth is fine. And then how would we find C? You can use Pythagorean theorem, but only if you use B in all of its unapproximatedness that's sitting in your calculator right now, not 13.8. You calculate with 13.8 using Pythagorean theorem because you're squaring and getting large numbers. That thing will be, that approximation error will be magnified enough to cause you to miss it. You can use Pythagorean theorem. You can also use a 12 and a C and this 41 because those are all not approximated, and use sine if you want. You could also use cosine with 49 to find it. You can use Pythagorean theorem, but to make sure you get that to the correct accuracy, you better make sure that this 13.8, when you use it, is what your calculator came up with, not the number 13.8. Does anybody have an answer one way or another? In other words, I could find it this way by taking the sine of 41 equals 12 over C. I could also take the cosine of 49 equals 12 over C. In either case, you'd have to cross multiply and divide. In other words, it will be 12 divided by the sine of 41, or it'll be 12 divided by the cosine of 49. Or Pythagoras will tell you the right answer as well. Whatever it is, what do you get?
18.3.
18.3 then, if we go to the nearest tenth? Did anybody find it this way, and do you agree? Yeah? Okay. Just show your work. So I can see what you did, patience. Okay, so far, not too bad, right? Trig, this is all trigonometry that you've had in geometry, except for number 2. Number 5 says, find the ordered pair on a unit circle, and that word unit circle is the most operative word in this sentence, the most operative phrase. Find the ordered pair of the point on a unit circle that is on the terminal side of and it will give you theta in radians. So here's the words again. Find the ordered pair of the point on a unit circle. Means the radius has to be 1. You have no choice. That's what the unit circle means. That is on the terminal side of theta equals, we'll try 5 pi sixths. So here's what you do. You sketch 5 pi sixths. Do you remember that that is pi sixth short of making it halfway around? Which makes it in the second quadrant. With what kind of triangle? Lay down or stand up? Lay down. This is 5 pi sixths. This point right here, if we are on a unit circle, must be, that point right there must be the point. Negative root 3 over 2, comma 1/2. Because this is negative root 3 over 2 when this is 30 or pi sixths. That's got to be negative root 3 over 2, and this has got to be 1/2 to get to that point. That's what you write in blank for this one. Now, what would you write if they had given you this theta? If they said theta is equal to 10 pi sixths. And that's not going to be pi sixths. Just happen to be hung up on pi sixths right now. Could be pi thirds, could be a pi fourths. But if it were 10 pi sixths, where would you be? And 10 pi sixths, by the way, is reducible to 5 pi thirds. Maybe we want to do that. You can write it like that if you want. It just occurred to me that's what I chose, 5 pi thirds. What quadrant is that in? Fourth, because it is a pi third short of making it to 6 pi thirds, which is 2 pi, right? So it's in the fourth quadrant with a reference angle of pi thirds, making it a, no, stand up. It's pi thirds short, so this is your pi thirds here. So it's 60 degrees, it's got to be a stand up triangle. Right?
Yeah.
So what is this point if this is the unit circle?
1/2 negative square root of 3 over 2.
Good. Sarah? No? In a stand-up triangle, the short side, and stand up or lay down either one, the short side's a half. And it's positive because you got to go right. The long side's always root 3 over 2. But it's negative because you got to go down. So you got to go out and down to get to that point. Got to go out a half and down root 3 over 2.
Okay, so on a stand-up triangle,
Or a lay down triangle.
so the short side is always a half,
Always on a stand up or a lay down.
and the long is.
Root 3 over 2. But you got to give it the appropriate sign. This one's negative because we go down. Yep. All right, now let's do one that isn't a stand up or a lay down. What if I told you that theta was 5 pi fourths? Where is that angle?
Third quadrant.
Think about it. 4 pi fourths would be pi, which is halfway around. You got another pi fourths beyond that. So it's third quadrant with a reference angle of pi fourths. You understand the counting? This is pi. This is 2 pi. This is also 4 pi fourths or 6 pi sixths or 3 pi thirds. This over here is 6 pi thirds, because that's 2 pi, or 8 pi fourths, or 12 pi thirds, or 12 pi sixths. Every one of those is 2 pi. And so when I was counting this one, for example, and I saw that theta was 5 pi thirds, I say to myself, that is either 2 pi thirds beyond this, or better yet, that is 1 pi third short of being 6 pi thirds, which means I'm pi thirds into this quadrant because I haven't quite wrapped all the way around and I'm pi thirds short of it. Okay. This one is pi fourths, 1 pi fourth beyond 4 pi fourths. So it's an improper fraction. So you say, okay, if I use up 4 pi fourths, since I know I got to go a little bit beyond that, what's left? Oh, a pi fourths. Then I'm going to go 4 pi fourths, and I've got 5 pi fourths into this quadrant, where the reference angle is pi fourths. Do you see it, everybody?
Yeah.
What
is this point then, if this has to be 1, and it does?
Square root of
Negative square root 2 over 2 over 2. Negative square root 2 over 2.
There you go. Because you got to go left and down. So they're both negative. Y'all see it? Okay, that's what number 5 is about. So it's just one to do, not 3, but I wanted to do several so you can see what's going on. Okay, boy, that's a mess. I got to get rid of everything here now again. Okay, number 6. Number 6 says domain and range of the function, and it is a sinusoid, but it is not just a typical one like sine or cosine. It's a transformed certain ways. So, what would be the domain of this? The domain of this. Well, what would be the domain of that? All real numbers. Good. What would be the domain of this one? So I've just given you one of the answers because I told you it was a sinusoid. Things that do this, and sine and cosine do this. They cover all the x's without a break. Okay. Now it'll be more specific than that. What I'm trying to do is get the point that it doesn't matter what these things are so long as this is sine or cosine, the domain will be all real numbers. Okay. It is more specific than that. It's something like this. The equation that you're supposed to be looking at. Y equals negative 5/4 times the cosine of x, just say 2x minus 5 pi. Okay, so what's the domain of this function? All real numbers, because it's cosine. So the domain, all reals. What's the range?
Negative 5/4, so negative 5/4 to 5/4.
5/4, less than or equal to y, less than or equal to positive 5/4. Or you can write it in interval notation, which is, now that you're grown-up mathematicians, is the proper way to write it. Either way is fine. Yes, it does. Yeah, it does. That's what happens when I'm talking and writing. I never get the details, but you're right. Yeah. Either way, you can write it either way, but interval notation is more grown up. And so you can see that if it's a sinusoid and you're trying to find the range, this has nothing to do with it because we don't care where you pick up that entirely continuous function that goes forever. We don't care if you pick it up and move it somewhere. It's still covering everything, and it's still from here to here. So that one's not very hard. You understand those two things. It's not those two things are not hard to understand. Huh?
All we're doing is finding domain.
That's all it says. Find the domain and range of the function.
Really easy.
It is. It is really easy. Okay. Number 7 is a little tougher. This is the one where they will give you one of the sinusoids and ask you to perform these transformations on its equation. So number 7 is kind of like this. It says the following transformations are performed in the given order. So make sure you do it in the proper order that they give it to you, the order they hand it to you, on a graph of y equals sine x. So they're telling you the parent function is sine x as opposed to cosine x. It's a sinusoid. And the transformations are like unto what I'm about to write. Not exactly, of course. A transformation is a vertical stretch by a factor of 4. B, I'm going to put parentheses on these so it doesn't look like a decimal. Okay. The B transformation is a reflection in the, which one do you want to do? Which axis?
Y.
The y-axis. Okay, C, so we got a reflection for B. A horizontal shift. That's called a phase shift, by the way, but they call this a horizontal shift in these words. To the left, pi sevenths. That's gross. And D, a horizontal shrink of 1/21. We have to do these in order. Vertical stretch by a factor of 4 does what to it?
Amplitude's 4.
Excuse me. Reflection in the y-axis will do what? Not the sign. What happens in here will be negative there, right? Yeah. It's going to reflect it over the y. Horizontal shift left pi sevenths.
No, it'd be minus.
Yeah, it's eternal.
Oh, then it'd be plus, yeah.
See what I'm doing?
Yeah.
And I'm leaving a space here because I've also got a horizontal shrink, which is going to go with that negative sign.
21.
Horizontal shrink, yeah, it's going to be 21 in here. Y'all know your transformations well enough to understand this is how it goes? And then if you write this, you'll still miss a point for not fixing it up. You got to clean it up by distributing inside there. So it's going to be 4 sine of negative 21x minus 3 pi. We've had these books that you're working out of right now for about 14 years. They missed the last adoption because we didn't have enough money to buy the upper books. Problem came up in the old set of books before you guys were drilled and killed on transformations. Everybody missed this. It was very difficult to convince people of how to do it. They all thought it was so hard. Now that you guys have been through the big ideas math, where you're doing transformations every other section, it seems like everybody gets this right. So it's what you emphasize, I guess. Are we okay on this? Do y'all see how it happened and things you're comfortable? So this is what you would write in the blank for these transformations. Any questions?
No. Wait, so we're
Mason's going, we
creating the
quit it, just go on. What? What?
Oh, I was just saying, sort of creating the graph, not writing the transformations.
No, you're not graphing any of this. You are writing,
You're not graphing.
you're writing the equation of the sinusoid.
That's what I meant.
Yeah. This is the answer. This is what goes in the answer blank. Okay? All right. Okay. Number 8. Number 8 is super easy. It really, truly is. It's as easy as number 6 was with the domain and range. Number 7 got a little complex, but you guys can handle it. You just got to go slow. Number 8 is pretty easy. It says, what is the period of this sinusoid? It's something like this. What is the period of, and we'll say it's a negative 4 cosine of 6x. And it says, what's the period of this function? That's all it says. What's the equation for period in general?
2 pi over pi.
2 pi over b. And do you know where to get b from?
6.
It's 6. It's the coefficient on x. That's b. And so the period is 2 pi over 6, which is pi thirds. Just like that. That's it. Right, pi thirds in the blank, you're done with that one. Now, if it doesn't divide nicely, like for example, if this is something strange like 11, then how will you answer?
It'd be 2 pi over.
Just don't reduce it. What you write? Okay, everybody okay on that one? No one, hardly anyone misses this one. If they miss it, they either didn't read it right or anyway. That's pretty easy. As easy as that one was, though, on the other side of the extremeness of easy to hard, number 9 is hard. And it's worth a lot of points. Worth 10 points.
10 points.
10 points out of about 55.
So if you don't get this one right, you're like, screwed.
If you miss it all, you're like, yeah, messed up. Most people don't miss it all.
Where are you gonna miss it?
Here's what it says. It says to explain how the graph of, and it will either be a tangent or cotangent. I can tell you that. Explain how the graph of, and I'll give you the equation in a minute, either a tangent or cotangent equation, is related to a basic trig graph. So if it's a cotangent graph and it's got all these transformations, then you say it's related to cotangent. That's the basic graph.
Wait, explain how the graph of blank is related. to-
Explain how the graph of y equals blah, 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 and it'll be the sine or cotangent, or a tangent or cotangent, I'll write it down in just a minute, is related to a basic trig graph. Meaning, how is this cotangent graph, or whatever, related to a basic trig graph? So you're comparing it to the basic cotangent graph, is what they're saying. You are to do these things. Determine the period, the domain, the range, the zeros, the asymptotes, if any, and then sketch the graph, 2 full periods. That's why it's worth so much.
Period,
Asking a million
domain,
things.
range.
So consider this graph right here, this equation. We'll say it's y equals, I'll give you your choice, and if you hit it on right, then this will be more like the one on here. Do you want to do cotangent or tangent?
Cotangent.
All right, y equals 3.5, no, I don't want to do that. I want to do something smaller, because it'll be a lot easier to graph. Let's do 0.5. 0.5 cotangent, you said, of, let's say, 4x. And then over here on the side, it says, because they didn't leave enough blanks for this, and so it looks really weird, but I'm going to write down what it looks like so that you're not flummoxed tomorrow. I have written, for number 9, I have written right here, the word period, I have written that down. And there's another blank underneath it that says D. And there's another one that says R. And another one that says zeros. And another one that says asymptotes. And another one that says, remember to label both axes in the graph. So I'm not giving you any chance to say, I didn't know I was supposed to do that. And then the other thing that they asked you about was to give the, let's see, it says, don't forget this, and it said, I have transformations. Yeah, so right up here, above the number 9, because there's no other place to put it, there's a blank that says transformations. And this is all handwritten by me. And then there's a blank extending out from here, and it says, don't forget this. And it has an arrow pointing to that. So that's what your answer thing looks like. And then over to the left of it here is a diagram that looks like this. So it's long this way. It's split right down the middle by a short y-axis. These are split up like this. This one's split up like this. And I really, really wish you would use my marks. You can use other marks, but I really wish you would have a label on the marks that I have. And we are to graph 2 full periods. Okay, here's all your given information. Now we got to go to work. What is the period of this graph? Because for tangent and cotangent, the period length is pi, not 2 pi, right? That's a big mistake people make. And if you make that mistake, it's going to throw your graph off entirely.
Okay, wait, so it's cotangent, tangent.
The period length is pi. So the formula for period is pi over b.
Okay.
So the period is pi fourths. Do I all see that? Yeah?
Yeah.
Because b is 4. Okay. Domain we might want to come back to. What do you think the range is for cotangent and tangent? All reals, because it just keeps going asymptotically top to bottom forever and ever and ever and ever and ever. So the range is all reals on this one. We'll talk about the domain in a minute. Let's pretend now that we wanted to start putting a graph together, because if we start putting the graph together, some of these other things will become clear. where do you want the asymptotes for this graph? If you want to do 2 full periods of it, where would you like to put the asymptotes? First of all, is there a phase shift? No, and there won't be. There's not going to be anything inside here to add or subtract. They're not going to add or subtract anything out here. They're not going to do that to you. It's going to look like this. These are the only 2 things that are going to be transformed. Okay, so where would you like to put the first asymptote for this function?
Negative pi 4.
Oh, add 0. If it were tangent, you would put it at negative pi 8 so that the period length could be pi 4 if it were tangent, but this is cotangent, right?
Yeah.
Now, how many periods do I want you to graph?
2.
Then where do you want to put the other or the next asymptote? To the right here? No, here. Because if you put it here and here, then in between these 2 asymptotes will be a period, and in between these 2 asymptotes will be a period, and you've used the graph efficiently. Now, if you put the next asymptote here and here, that's fine. That means the next ones go here, and you'll have room to put 4 full periods, and I expect you to do that. If you're not going to spread it out properly.
So for tangent, the first one would be on the second dash, then the first dash.
For tangent, the asymptotes would be here, and the next set here, and you'd probably have to do, I guess if you did 2 full periods and left a little bit of the graph off, I'd be okay with that. But you have to straddle the origin when you're doing tangent. The asymptotes have to be this far left and this far right so that the distance between them is pi 4. So this would have to be negative pi 8 and this would be pi 8. But
So if it was tangent, you would have 3.
yeah, you would. And you could do 3 or just give me 2. All it requires 2, any 2 you want. Okay. But this is cotangent. You see where I placed the asymptotes?
Yeah.
What is this one labeled? So we're starting to label the axes now.
Pi 4.
Pi 4ths. So that this period length is pi 4ths. This one is pi 4ths. So this is pi 8, and this is pi 8. Okay. And how are we going to instigate the rest of the graph? How are we going to put it together?
Isn't it like, so pi 8 is is where it intersects the x-axis, something like you go like, since the period is, not the period, it's sort of vertically shrunk by 0.5, you go halfway between pi 8s and pi 4s, and then
Yep.
go up 0.5, right?
Yep. So you would go from here where it's going to cross. And when you come back here, this cotangent, does it start high and end low or start low and end
Oh,
high?
that's right, it starts low.
Cotangent starts high and ends low. So from here to here, when I go halfway, I'm going to go up to here. It's going to be up there and down here. Because it's got to start high and end low. Cotangent does that. Yeah? Okay. So this one's going to go halfway out, and we're going to go up or down? Down. Half. Do y'all understand why a half? You see why I'm going down?
Yeah.
Because cotangent starts high and ends low. So over here, halfway out, I'm going to go up halfway. And that's going to be a point on the graph as well as this one. And so my graph is going to bend hard on its way up to that asymptote. Same thing here, because of that 1/2 makes it bend hard. It's been squashed vertically. So there's the graph if these are numbered by 1s. Now, if you had a half right here and you didn't want to bend it quite that hard, then you could number this a half. As long as you numbered it and I could see what you did, that would be fine. I didn't. I assumed these were 1s. So I should have a 1, 2, and a 3 here, and a -1, -2, -3, the way I built my graph. If you want to let this be a half and this be 1.5 and this be 2, then you need to number it that way so that I can see over here that you went up a half of whatever it is that you numbered it with. These are, everything in the red is stuff that you produce. The black is all you get. You just get marks. You got to number appropriate to how you built your graph. So the way I did it, I assumed this was 1, so I only went up a half. There. You understand what I'm saying? Yes.
Is the reason it's going like up and down a half each time because of the 0.5?
Yes, because of this right here. You go out from the 0 marker, which is right smack in the middle between the asymptotes. From there, you go out a half. You go halfway out and down this if you're doing cotangent. If we were doing tangent, which goes like this, you would go out halfway from here to there, and you would go up a half so that it would bend this way. You with me? Okay. All right, so the graph is done. Now let's see if we can tell from this. What's the domain?
All numbers except.
You're trying to figure out how to phrase it so you don't include the asymptotes, right? Which is correct. That's what you should be thinking about. What? An asymptote occurs every time there's another pi fourths. So the next one will occur at 2 pi fourths, right?
Yeah.
And the next one 3 pi fourths, and the next one over here. So yeah, and you can actually write it out in words. That would be fine. You would write x, not with that marker, x not equal to, because you're trying to cut things out of the domain. Integer multiples of pi halves. You can write it like that. Here's another way to write it. If you want, if you like the little more mathy way of doing it, you could say,
Wait, what's the pi
I'm just
half?
gonna write or, this will be perfect.
Would it be pi fourths?
It's pi 4.
Yeah, that's right,
Okay.
like I say, thank you, because that's what I get for top of the line, right? Thank you, okay. You could also write it this way, x not equal to n pi fourths, n an element of the integers. That's another way of saying
Okay, so not that.
it's shorter, but that's the mathy notation for doing it. One way or another, you gotta indicate that it's integer multiples, because if you multiply pi fourths by something other than an integer, like 1/2, you wouldn't have the next asymptote. You have to multiply by whole numbers, positive and negative, to get them all. You see what I mean?
So we
So
don't
you've gotta say, I've gotta multiply an integer by this to get the next one.
Sorry, real quick, going back to the, vertical stretch.
Yeah.
Are you always gonna go out halfway though?
Yes,
Okay.
halfway and go up or down the stretch or shrink. You just got, but if it's cotangent, you gotta go, when you go left, you gotta go up. When it's
Yeah.
tangent, you gotta go left, you gotta go down.
So if it was like
Correct.
4 instead of 0.5,
Mhm.
you would still
You would
go
go-
out.
You go halfway out and clear up to here to put a dot.
So you're always gonna go out a half and then
Yep.
whatever. it's-
That's gonna be your first jump. And you're only gonna need 3 points in your asymptotes to make it bend properly. It's gonna work out.
Okay.
Everybody clear so far?
Yes.
So where are the zeros?
Pi eighths and
Negative pi
negative
eighths
pi
and
eighths.
At pi eighths, will the next one be at 2 pi eighths?
No,
No, because here's 2 pi eighths. Where will the next one be?
every odd integer.
Every odd multiple of pi eighths.
So do we need to write that or can we just write down negative pi eighths and pi eighths?
No, what you have to do is write, you could write it like that or like this. You could say integer, I say odd. The zeros occur at x equals, yes, at x equals, yeah. X equals, not equals, because we're trying to include them this time. X equals odd integer multiples of pi eighths. You could also write this. X equals n pi eighths n, an element of the odd integers.
That's my brain.
So you gotta be kind of mathy about this. Asymptotes occur where? This one's easy
Isn't it
Negative
just
pi
the same
fourths.
domain?
because we've already identified where the domain is not defined. That's where the asymptotes are.
I just take out the.
Just take out the not equals.
Yeah.
X equals n pi over 4, n an element of the integers. That's why the asymptotes occur. Those are the equations of them. Okay, so the only thing we haven't done, and I said, don't forget this when we haven't done that yet, is the transformations. What list of transformations will you say for the basic cotangent function?
Vertical shrink is 0.5, horizontal shrink is 1/4.
You can abbreviate it the way I did, but the one thing you can't cut out of it is the V and the H. You also can't cut out the H's at the S. You can't say a VS because stretch and shrink start the same thing. So you've either got to write ST for stretch or SH for shrink, and you can abbreviate them that way, but don't abbreviate them so tight that I can't tell what you mean. So that one's complete. That graph is worth like 3 points, and each one of these, let's see, 1, 2, 3, 4, 5, 6, yeah. I think this one might be worth 2 points because it's got 2 things in it, and every one of these is worth a point.
What is it in the asymptote one when it says x equals n pi, what is n?
It's a number that's an element of the integers.
Um,
Means you have to multiply pi fourths by a whole number to get the next asymptote. This integer, or this asymptote right here, is at pi fourths times 0. This one is at pi fourths times 1. The next one will be at pi fourths times 2. This one was pi fourths times -1. The next one will be at pi fourths times -2 will be the next one. And so you always have to be multiplying by an integer, not some other number. That's the reason why we have this. This fat-sided z means we are going to restrict our multiplier to integers, not fractions or irrational numbers. You know what I mean?
So when we write the asymptote one, we have to have that n e z thing too.
Yep. Yeah. If you just write n pi fourths and you don't include this and you leave it out here, it'll probably just cost you a point for both of them. But you need to indicate that what we multiply pi fourths must be an integer as opposed to other numbers. Otherwise, we won't get to the next asymptote properly. Okay? So you can write int like you want, indicating you mean integer multiples of pi fourths. If you want to write it out in words, that's fine.
Oh.
Okay, that's it for today. We will talk about 10 through 15 tomorrow. And there will be another piece of this video without time. See ya.